Today let's talk about planar graphs. So graphs, of course, are just vertices and edges, and we draw them typically in the plane by drawing a bunch of circles or dots to represent vertices, and then we connect them by edges. Right? So of course, when we draw a graph, the vertices and the edges which connect the vertices could be drawn any which way we want. For example, here is a graph with 4 vertices and it's got 4 edges, and we notice that the way we drew this, these two edges actually intersected in this place. Okay, but that is not an actual vertex of the graph. It's just some point at which the two edges intersected because of the way we drew it. Okay, so we could equally well have drawn this very same graph in such a way that these edges don't really intersect each other. So I have this, and then the fourth edge, I could draw it like that. Okay, so now observe, I drawn the very same graph with the same vertices. So let's number the vertices 1, 2, 3, and 4. So I still have 1 being connected to 3, 2 being connected to 4, and 1, 2, and 2, 3 being connected. But the way we have drawn it such that they did not intersect. Okay, so this sort of configuration is what a graph which allows for a drawing in which the edges do not intersect is what is called a planar graph. Let's try and define this. So we say, so a graph G is said to be planar. Planar if it can be drawn on the plane, as we usually do, on the plane, such that no two edges intersect except at a vertex. Okay, so these sort of extra intersections that we saw in this case, this additional intersection that was actually not a vertex but just something which happened because of the way we drew the edges, that sort of thing does not happen. Okay, meaning it is possible to draw the graph in such a way that that does not happen. That's the exact definition. Okay, so what is an example? Well, any tree, for example. So if you take G, so we've just talked about trees. So if you take G to be any tree, okay, so recall a tree is just a connected graph which doesn't have cycles, then any tree can always be drawn on the plane such a way that the vertices do not intersect. For example, so no matter how large the tree is and no matter how the vertices and no matter how many vertices it has, you can always draw the tree on the plane such a way that no two of the edges intersect. Okay, now this is an example of a planar graph. There are of course other examples. Now for example, G can be just a cycle. So a cycle, recall, is just a graph like this with n vertices sort of arranged in the form of a circle. So that's again a planar graph. So there are many other examples of planar graphs. So let's draw one more. So I put in a cycle. Maybe put in a few more cycles. You could have a tree-like thing inside, and so on. So there are, you can imagine doing a bunch of things like this. So here's an example of a planar graph. Now, the first thing that one observes, and one of the sort of important things one observes when one has a planar graph, is that it somehow divides the plane into various what we would call regions or faces. Okay, so if you have a planar graph, you automatically have the notion of regions or faces of the graph. Okay, so what do I mean by that? So it is sort of a subset of the plane which is sort of bounded on all sides by the edges of the graph. So here is one region. So let's maybe number the regions. So here's region number 1, here's region number 2. This entire thing here is region number 3. Okay, it's got a few edges sticking into it, but still this entire thing is bounded on all sides by edges of my graph. So that's region number 3. And well, in a sense, those are the only 3 bounded or finite regions. And in addition, we say, okay, everything outside is thought of as this is the exterior region or the outside region. So this is 4, this is the exterior region. So we think of these as being the regions of a planar graph. So let's look at the earlier examples. If I had a single cycle, then there is one inside region and one outside region. So there are 2 regions here. And in the case of a tree, there are no inside regions. You've only got an outside region because there is no region which is completely surrounded on all sides by the edges of the graph. So for a tree, you've only got one region. Okay, so these are the examples of regions that you have as soon as you draw a planar graph on the plane. Okay, now here's sort of an important theorem which you probably have seen in other contexts. So this is a very important statement called Euler's formula for planar graphs. And what Euler's formula says is that if G is a planar graph, and you have a certain way of drawing it on the plane, so imagine you have drawn it, then the number of vertices of G minus the number of edges of G plus the number of regions or faces of G is always 2. Okay, where so V and E, of course, we know what they are, vertices and edges. V is the set of vertices, E is a set of edges. So all this is of the graph G. And F is the set of faces or regions of G. Okay, so let's just again see this by example in the earlier instances. So if you look at this graph here, it's got 4 faces. So first let's write down faces, that's easy to count. And let's look at the number of vertices. So I have 1, 2, 3, 4, 5, and 6 in this cycle. Then there's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, then 19, 20, 21, 22. So I've got 22 vertices in this case. And let's count the edges. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, and in this case 22 minus 24 plus 4, So that's 26 minus 24, which is exactly 2. Okay, so that's what happens in this case. If you have a cycle, so here observe in a cycle the number of vertices is equal to the number of edges. So that's always the case if you have a single cycle. So here there are 4, 5, 6, 7, 8 vertices, and I've got 8 edges. So 8 vertices, 8 edges, and the number of regions is 2. Okay, so again V minus E plus F is 8 minus 8 plus 2, which is 2. And in the case of a tree where you have no, there are no interior regions, only one exterior region, observe we proved if you have a tree, then it always has vertices equal to edges plus 1. So that was one of the various characterizations of a tree, that it is a connected graph which has mod V is mod E plus 1, or that it is an acyclic graph with mod V equals mod E plus 1. So here again, it doesn't matter how many vertices and edges it has, they both always satisfy this relation, that vertices is 1 more than edges, and faces is always 1, right? So this is always going to be 2, because here F is 1. Okay, so in all these examples, at least we have checked that Euler's formula holds. Now, let's see how one would prove a statement like this. Okay, so the proof is like in the proof for the characterization of trees, it's going to be an inductive proof. Okay, so the idea in many of these cases is you sort of construct bigger graphs from smaller ones, or rather given some planar graph, you try to remove some vertices or edges or faces or something in order to get a smaller graph for which you know the required statement by the induction hypothesis, and somehow you try to use that to prove the original statement. So let's do induction, proof by induction, and again we have maybe a few different choices on what to use as our induction parameter. So let's use n to be the number of edges. So we're going to do induction on using the number of edges as our parameter. So what does that mean? So if we take, so let's just start by looking at the base case of the induction. So first we have to establish it for n equals 1. That means I'm looking at a graph which has got just one vertex. So I forgot to say in this case, when I say planar, of course we always mean it's a connected graph. Okay, so in my definition of planar, I really mean connected. So, but let me just put that in as for emphasis. So I have a connected graph. It's planar. It's got only one edge. So what can that look like? If I only have one edge, then that's the only thing I can have, right? Because I've assumed it's a connected graph. And in this case, it's of course a tree, and vertices is 2, edges is 1, and faces of course is just 1. The one exterior face. So this is 2 as it should be. So we have proved it in the case of n equals 1, number of edges equals 1. So now let's assume that this is true for assume true for all planar graphs with less than or equal to n edges. So I'm going to use maybe strong induction. No harm in assuming this. You could also do it with just 1, for example. So anyway, let's just do this. Assume true for all planar graphs with less than or equal to n edges. And so what is n here? So now we'll assume that n is 2 or more. Sorry, n is, let n be any number that's 1 or more. So we assume it's true for all these, and then we will show it's true for a graph with n plus 1 edges. So now let G be a planar graph with n plus 1 edges. We will try to show that the same conclusion, the required conclusion, holds for G. Okay, so how should we do this? So the idea is, how do you go from this given graph with n plus 1 vertices to a graph so with n plus 1 edges to a graph with just n edges? Well, you try and remove an edge, right? So that is the idea. So so let's look at two cases. So what is the case we really care about, the thing we are thinking about? So if the graph G looks like this, so it's got a cycle, maybe it has many cycles. So let's say your graph G looks like this, then the idea is to try and remove an edge from this graph. So let's just look at this situation. So let me say here's case 1, the graph G contains a cycle. So if that happens, then, so what I want to do is to choose an edge, say this one, and delete it. Okay. So when I delete it, I'm going to get a new graph. So let G hat be the graph obtained from G by deleting an edge of a cycle of G. Okay, pick any cycle and pick any edge from that cycle. When you do that, you now delete it and you get a new graph. Now, what has happened to this new graph? Firstly, the number of edges in this new graph is 1 less than the number of edges in G, so it's got only n edges. What else do we know? We know that the number of vertices has not changed. So, sorry, I should have written cardinality of the edge set is n. The vertex set does not change, it's the same set of vertices as before. And what's happened to the faces? Now observe that when I take something in a cycle, an edge in a cycle, and I delete it, what I'm essentially doing is opening up that cycle, right? So my new cycle, the cycle now no longer has that edge, and it sort of has a hole there. So what's happened is that this original region here is sort of merged with the region adjacent to it. So this holds no matter what. I mean, here it merged with the outside region. It could also happen that maybe instead of this edge, I deleted this edge in the middle. So imagine that I had deleted that edge. Now all that will happen is that this original region merges with the region, the closed region which is adjacent to it. So removing an edge essentially ends up merging two regions. It can be two closed regions or one closed region with the outside region. So in other words, the number of faces of G hat also reduces by 1. Faces of G minus 1. So observe, edges of G is edge of G minus 1, which is n. Okay, so now in a sense, we are ready to apply the induction because G hat has only n edges, so you can apply the induction hypothesis. And if you observe, G hat and G, how do they differ? They have the same number of vertices, one less edge and one less face. Okay, so now apply induction hypothesis. To the graph G hat. Now conclude that number of vertices minus edges plus faces is 2, but this is the same as number of vertices of G minus 1 less edge plus 1 less face. And the ones are, I've subtracted 1 from the edges and 1 from the faces, and observe that the plus 1 and the minus 1 cancel each other. And from that, you conclude that the same conclusion holds for G. So this is what you had to prove. So get done. Okay, so that completes the proof of Euler's formula. So we talked about planar graphs and Euler's formula. So here is an example. So we looked at many examples of planar graphs. Here is an example of something that's not planar, and I'm not going to prove this, but maybe let you think about this. So the idea is the following: just take 5 vertices. So 3, 4, and 5. And now what I'm going to do is I'm going to connect, everything, every vertex to every other vertex. So if we sort of do that, get this kind of 5-pointed star inside this outer pentagon. So there are 5 vertices, 1, 2, 3, 4, and 5. Now, what is this? This is sometimes called the complete graph. That is, you draw 5 points and you join every vertex to every other vertex. So this is sometimes called K5, or the complete graph on 5 vertices. And here is maybe a challenge. So try redrawing it in various ways. See if you can manage to redraw it in such a way that, redraw it on the plane in such a way that no two of these edges intersect. So the way I've drawn it is pretty bad. There are lots of intersections. This is not a vertex, but these 2 edges intersect here. So I've got these intersections in the middle. So the question is, can you cleverly draw it in such a way that all these intersections vanish? Okay, it turns out it cannot be done, but you should try and draw as much of the graph as you can without needing, without having intersections happen. Okay, so you see how much of the graph you can draw. How many of these edges can you totally draw? So if you count how many edges this has, this actually has 5 choose 2, because you have connected every vertex with every other vertex. So there are actually 10 edges. And out of these 10 edges, see if you can at least get 9 of these edges to be on the plane without, without intersection. Okay, so this is not planar. Okay, but here's sort of the question or challenge, problem, delete. Try drawing the resulting graph on the plane. Such that no 2 edges intersect. Okay, so see how you can do this.